Hello and welcome back to yet another lecture on the NPTEL course on advanced plasticity of solid continua. Now, if you recall, we have been discussing about rate dependent plasticity for some time. Specifically, we will now discuss rate dependent thermo-viscoplasticity. So, rate dependent viscoplasticity we have been discussing. We have actually a way of posing all our plasticity problems that we have encountered so far within a variational framework. So, as you have probably realized by now that the advantage that accrues in the process is that just like an elasticity problem where by taking the variation of the strain energy functional you can get all your solutions even in a discrete setup by finite element method, for example. Here, by taking the variation of the rate functional, you can exactly do the same thing. And in deriving this rate functional, the convex analysis has played a major role. Okay, so we will be discussing the variational problem associated with thermo-viscoplasticity as well. Okay, so let us come to the details now. First of all, we have to have temperature as one of the variables in our setup, so it may turn out therefore, because in many cases it has been seen that the so called yield stress may depend on temperature. Please note that yield stress is basically not a stress, it is just a material parameter. So it depends on temperature. This temperature is the absolute temperature here. It is called theta here, as you can see here. So, if we call by sigma the stress, the usual the notion of stress, x the back stress and probably other variables. Basically, the other hardening variables are included in alpha. So I should write it as f of sigma x alpha theta ideally. So anyway, I mean wherever we need things we will use. Okay, so but for the time being what we are doing is that we will include all these unknowns associated with that is the internal variables, force like internal variables associated with plasticity within x. All right, so that the internal variables of the kinematic type like the plastic strain rate and all that will be within alpha. So in that case we can actually forget about this alpha dependence of f, because f is typically a description of stress like things, right? That is, the yield stress should not be exceeded or that sort of statement, right? So anyway, so with that caveat, let us assume that f is a function of sigma x and theta. I will repeat, okay, so x contains all the force like thermodynamic force like variables which are conjugate to the actual rate of the internal variables alpha. That means x is thermodynamically conjugate to alpha dot. All right. So in this case we can actually starting with some phi star as here, right. Here you remember that phi star, probably we discussed some of this in the last class. This f is basically the yield function. This is a Perzyna type viscoplasticity, so the notion of an yield function still is there. Now this k theta is a stress like quantity, okay, it is something like a dynamic overstress you can say, so that f and k have similar units, right. M is the exponential rate sensitivity parameter and mu is the viscosity parameter which also can depend on theta. Okay, so k can depend on theta, mu can depend on theta. Okay, so now you understand that if I have to do, this is phi star Vp, right. So if we take a Legendre transform of phi star Vp, it has to be with respect to the supremum's argument which is here has to be minimized or maximized with respect to both sigma and x, all force like quantities, that is all stresses, right. Sigma is the usual stress, x is the thermodynamic force. So, in other words, what I mean to say is that there are now multiple variables over which the supremum has to be taken. Now, the trick is to reduce the above maximization to a simpler problem, such that instead of doing all this, we can actually minimize this argument with respect to just a scalar variable, call it s or something. Okay. So, let us see how we can do this, right. So, first define the overstress. So, as you know that F in Perzyna type viscoplasticity, in all viscoplasticity, F can be greater than or equal to 0, right. There is no reason that it should be less than 0 all the time, and the value that it exceeds 0 by is exactly the overstress. So, S, whenever F is non-zero, F exceeds 0, that is S, the overstress. Now, the convexity and the normality, that is the fact that the gradient of F with respect to sigma and x is normal to the surface defined by x, F, for any given F equal to some number. Okay. So, that surface is, if you call it the generalized yield surface, then del F by del sigma and x, that is the gradient of F with respect to sigma and x, will be normal to it, right. That is the normality rule. So, it is not a rule, it comes automatically due to the property of the gradient, right, being normal to the surface. This imply that the maximizing pairs sigma and x, which appear in the argument of the supremum in the last slide, that must align with the gradient of F, right. So, therefore, we can say that these quantities, that means sigma inner product with epsilon p dot is the plastic strain rate, the thermodynamic plus the thermodynamic force dot product with alpha dot, alpha are the internal variables like epsilon p and other hardening variables, must be equal to some s, that is, which is F, times some lambda. So, basically this lambda is in this particular case called the generalized plastic multiplier. It is the dual norm, it is basically the norm of this combined thing epsilon p dot and alpha dot. But since epsilon p dot and alpha dot are thermodynamically conjugate to sigma and x, so therefore, we use this dual norm here, right. I will explain what this dual norm is soon. Okay. So, this is the dual norm. You remember that in general, the usual perfect plasticity, the norm of epsilon p dot itself is sometimes called the plastic multiplier. So, here that is generalized to a more general statement, like it is not just epsilon p dot, but also alpha dot that comes into play. So, let us talk a little bit about this dual norm, right. So, you know that the so called elastic domain is given by this set C theta. Now, this set can be a function of theta also, because temperature dependence has entered everywhere. This is for all sigma x for which F is less than or equal to 0, right. So, we also require that this yield function is convex in all these thermodynamic forces like sigma and x, and because it is basically represents the rate independent part of this dynamics, so it is positively homogeneous of degree 1, because as you know in rate independent plasticity the yield function is positively homogeneous of only degree 1. Okay. So, C theta is a closed convex set containing the origin, that also we must ensure that it must contain the origin of what? Origin of sigma and x, that means sigma equal to 0, x equal to 0, right. It must be included within C theta. Now, if you actually think of this is an interesting concept, it is called the Minkowski functional. I will explain this to you. That means suppose this is my, think of von Mises plasticity, this is my yield set C theta, right. So, this is my C theta, correct. The thing is that this is the yield surface, this is F equal to 0, right. Now, this is viscoplasticity. So, there is no reason why the stresses should be restricted only within the yield set, it can cross it. Suppose the origin is part of it, right, as we have already seen, I mean we have taken it, ensured that origin is part of this C theta. Now, let us say the stress is here, right. Stress here means not just sigma, but also x, force like objects, right. So, everywhere, this is, so if the stress is here at this point, then it would mean that there will be some kind of, a multiplier of the set C, a scalar multiplier, by which if you multiply this, it is like a circle, right, C theta is a sphere. If you multiply it by a scalar, typically if the scalar is greater than 1, then this thing will increase, right, it will become a bigger sphere. Now, the thing is we are interested in that particular factor which multiplies C theta such that this sphere goes through this stress, right. That means the minimum value of this multiplier for which this stress or this generalized thermodynamic force is within this lambda or gamma times C theta, right. So, this is what actually is given here. So, the norm, or you can call it the Minkowski gauge of sigma and x corresponding to the set C theta is the infimum of all such scalars gamma greater than 0 such that the inner product of sigma and x must belong to, or sigma and x itself, sigma and x as elements of this thermodynamic force must belong to gamma times C, all right. So, this is a very important thing. This gives a, first of all it gives a norm, right. Basically, I do not want to get into further details because it will further confuse you. It is a semi norm, but I am not getting into the, so it is a norm like quantity. The second thing is that it also is very physically meaningful, all right. So, corresponding to this, you can see that if I define this Minkowski functional this way, what we are finding, this is the infimum of all this gamma, right. What is this gamma? This factor gamma which multiplies this C. You can easily see from the physical perspective that this gamma, which is the this Minkowski functional, is nothing but the overstress itself, right, because that is by how much it has exceeded F equal to 0. The stresses, I mean the function F have exceeded F equal to 0, right. So, this is basically the idea of the Minkowski functional. Now, based on this we can define the dual gauge or the dual norm. This will be applicable not on the thermodynamic force like quantities, but on the internal variables, that is rates of them actually, because these are the rates that produce dissipation. So, this is called the dual norm on epsilon p dot, which is one of these rate of the internal variable, alpha dot another rate of the internal variable. So, this dual norm is defined by, right, you have to actually take the supremum, this is something like the dissipation, right. So, sigma times inner product epsilon p dot plus x dot alpha dot is like the dissipation. Now, for a given epsilon p dot and alpha dot for which you are finding this left hand side quantity, you have to find all sigma and x for which this is the maximum, this is the supremum. So, that means when you find that sigma and x, the dependence of this whole quantity on this, on the left hand side, on sigma and x vanishes, right, because you have found a specific sigma and x for which this is the supremum, right. So, it is only as expected a function of epsilon p dot and alpha dot, right. So, as you can also remember carefully, if you remember what was the, when we discussed rate independent plasticity, we defined the support function, right, of a set, and that gave the the support function was the dissipation function for us in rate independent plasticity, right. So, you can see from the definition of this is nothing but the support function of the set C theta, correct, you remember, right. So, if you do not, please go back to our definition of support functional and how we relate it. We call this HC or something, the support functional of the set C, right, of a function of epsilon p dot, right. So, if you do not remember, please go back to that lecture and refresh your memory, because this is very useful. You will not be able to relate it otherwise, okay. So, you can see what we are basically talking about as the dual norm is basically the maximum mechanical power that can be delivered given any admissible, given any epsilon p dot and alpha dot, right. That is the maximum mechanical power for a given rate, right. Now, having realized this, we can, let us denote by lambda, right, as this dual norm of epsilon p dot comma alpha dot, right. You will now easily see, because that this dual norm is nothing but this support function over the set, over the yield set C, this lambda is just nothing but it is related to the rate independent part of the phi, correct. It is basically related to that, it is nothing but exactly that. So, phi, that is the dissipation potential in viscoplasticity or thermo-viscoplasticity, has two parts. One is the rate independent part, the other is rate dependent part. Of course, there will be also now a thermal part, that is different. So, the rate independent part is clearly given by this lambda, all right. Now, let us actually now do this, if you now go back to this particular this statement, right, that lambda times S was the overstress, lambda is the dual norm of the rate type variables. If you multiply these two scalars, you get basically the dissipation corresponding as if to the rate independent case, right. So, this particular thing can now be used to define this. So, you can see that whatever was there in this this part, okay, this part in the phi Vp, that is during the Legendre-Fenchel transform of phi star Vp, this first part is nothing but lambda times S, right. Okay. So, you see that now I can write this phi Vp as the supremum over this simplified thing, where my objective now, this phi Vp is basically a dissipation functional. So, it must be a functional of rate type variables, right. So, therefore, it has to be a functional of rate type variables means lambda. S is a stress like variable, even though it is a scalar, it is an overstress, right. So, supremum over all S has to go out, okay. I mean, after doing the supremum, the left hand side phi Vp will not depend on S anymore, right. So, supremum over all S greater than equal to 0, because it is the overstress of this quantity, okay. So, you understand that what we wanted to do is to reduce the complexity of my minimization. It is not a great deal of, I could have easily done even that complex minimization, but this becomes easier, okay. Now, this is a much easier problem. So, you can actually simplify the above. This basically you see that there is a k theta here, k theta here. These are all very standard things. I would actually ask you to do these things on your own, try to understand them. The simple algebra, you can actually, if all these derivations you should try and do it on your own. It is also possible that despite my best efforts, there may be one or two errors, you may be able to find it. Okay. So anyway, so now we can actually simplify this above, this way. This is my final form. I mean, this is not the final form. I can further simplify it by taking this as A, okay, call this as A, and then you can actually do the minimization. This is the minimization of this with respect to S. That is what we need. So, the stationarity condition, differentiate with respect to S, there is no difficulty in differentiating. So, therefore, it becomes lambda is found in terms of S, or rather the other way, the S is found in terms of lambda and A, which is here, okay. And you expand by substituting back for A, this is the scenario. So, you can now write lambda S for this particular S that maximizes the argument, which is this, right, and you write the other part, which is basically the rate dependent part of phi Vp, also by substituting this specific S, which is this. Put all these things together, then you get phi Vp is this. But of course, I mean, you understand, you recall, please recall this is very important. Then we have found phi Vp, but we have also to add the phi Ri, the rate independent part. And also recall that even though we add phi Ri, there is no phi star Ri, because phi star Ri is either 0 or infinity. So therefore, we started with phi star or phi star, and there was no Ri there. There was no rate independent part of the phi star, right. So we have actually got the rate independent part, or a non-trivial expression for the rate independent part only in the dissipation potential, not in its dual. So add phi Ri, which is basically nothing but the support function of c theta, okay, over sigma nx, find the supremum. This is nothing but the dual norm. We called this as lambda, remember, okay. So find this. So this is my phi Ri. So you can add this phi Ri to the phi, and also add an extra term corresponding to, as you can see, the extra term corresponds to the heat transfer. Okay, k theta is not exactly, but related to the conduction coefficient. Now, and q is the heat flux. This is the rate dependent part. You see that if mu is 0, then we recovered the rate independent plasticity, that you must always remember, okay. And lambda is the dual norm. So this is my scenario so far, okay. Now let us take a look at, because we have been discussing about yield functions of this kind, in which f is a function of some sigma, x, theta, etc. But we have not talked of very specific forms of f which we can make use of in deriving my Perzyna type models actually before implementing in a computer. We must talk about a few very well known such yield functions which are used with Perzyna type models, okay, in practice. So let us talk about that now. So let us, that means we are talking about various yield criteria with temperature dependence, right. So that yield function defines also corresponds to the rate independent part in the dissipation potential, please recall that. So all the functions that I am talking of here are basically extended von Mises type. We are not talking of any non-smooth type of f, okay, because it will make the analysis more difficult. By now you know how to do it based on this convex structure, of F, even if it is non-smooth, but I do not want to unnecessarily make things consistently difficult by talking about non-smooth F. So, let us talk about only the smooth F, and many such Fs that are used in practice are basically smooth. Okay, so that fit with the within the Perzyna framework, okay, those Fs. So, first define the effective. So, now let us say, so there are some small variations in my notations, so please do not get confused. So far we were talking of X as the thermodynamic force, of course it is, but now we are talking of X as the specific thermodynamic force which corresponds to the back stress. Okay. So, I mean, of course, I mean there is no great change in our notations except that we now identify X with the back stress. Okay. The corresponding, you know, the hardening part corresponding to isotropic type of hardening will be determined through these alpha like variables, right, okay, the kinematic like variables. So, sigma effective therefore is the, you know, repositioned sigma minus x. Its deviatoric part, you know, typically we have been writing sigma 0 as the deviatoric part of sigma right, but here if I put sigma effective 0 it becomes more complicated. So, I just wrote sigma effective dash, right. So, that is the deviatoric part of sigma minus x, right. So, x represents the back stress due to kinematic hardening, okay, and also denote by the effective, you know, von Mises stress, this factor square root of 3/2 if you want you can put, otherwise you can also absorb it within one of your parameters like sigma y and things like that, okay. So, this factor is not always necessary, it is provided you do it correctly, okay. So, if you can absorb it within one of the parameters then this factor is not needed, okay. So, this is my effective von Mises equivalent stress, okay. Now, let us talk of the first von Mises type isotropic hardening which is temperature dependent. For that the F is given by this effective stress that we just talked of, the Q effective equivalent stress rather, okay. So, sorry, the Q is the equivalent stress, a function of sigma minus x, minus this sigma y now is a function of both alpha which is responsible for isotropic hardening and absolute temperature theta, okay. A typical choice for sigma y, which is the most important thing the choice of sigma y is mostly the most important thing here. Now, because it is a function now, it is no more a parameter, right. Our first model in rate independent theory was such that sigma y is just a material parameter, but no more, okay. So, our function sigma y is could be of this form, sigma 0 which is the initial yield stress, right, and not the I mean not the, you know, deviatoric part of the stress. So, maybe I should call it sigma y 0 or something, but remember this, okay. So, H alpha is basically the hardening part, the hardening isotropic hardening contribution to sigma 0, whole thing is multiplied by some temperature dependent r theta, all right. So, H alpha is the isotropic hardening, it can be linear or saturation type hardening. We have discussed both these hardening types earlier. If you do not recall, please go back. See, this is the way of actually learning this. Repeatedly go back to the previous slides or previous lectures and then come back whenever you forget anything, okay. So, this is one advantage of this online thing, even though there are disadvantages as well. So, r theta is basically called the thermal softening function. It is typically responsible for softening because thermal effects typically cause softening, okay. The common choices are it could be a linear in theta as here in the first case, it could be exponential in theta, you know, theta 0 here is a reference temperature, or it could be power law in theta, okay. So, all three are possible. This applies to metals under moderate temperature variations, you know, these are the typical temperature variations you will see in practice, including the cases which often undergo extreme plastic deformation like manufacturing, forging of components and things like that, okay, metal forming. Even in those cases this could be applicable, right. Now this is a very famous, for metals, after World War II, this kind of a thing was developed by Johnson and Cook. And that tells you F is of the following form: Q as before, okay, the equivalent stress. Now you can think of this as the initial yield stress, which could be A is something like that, B is another constant, alpha is that hardening, isotropic hardening, kinematic variable, all right. So alpha to the power n is a material constant again. Then this is a rate term, the point, and this is the temperature softening term, right. T star is given by theta minus theta 0 divided by theta m. Theta 0 is a reference temperature, theta m minus theta 0 in the denominator, and you have theta m as the melting temperature of the metal under consideration. The thing is that this part, which is typically called the rate dependent part, we already have separated that. I mean, here it is not separated. You understand? We have separated the rate dependent and rate independent part in phi. Correct? So in most cases, when you use this in our context, it is best to take it out, because our rate dependence is anyway there in another part of phi, and just consider these two factors. That would do the job. Okay? So we may drop that logarithmic rate, right? But original Johnson Cook was not like that, because it was done at a time when things were not that developed, and this worked very well, for a long time, right. So even today many people, many researchers including, they use this directly, okay. So the remaining terms, this term gives the thermal softening, this term is basically the strain hardening part, all right. So we will be discussing, so we have so far discussed in this course, in this particular lecture, the initial aspects of how to define, starting with a phi star, how to define phi Vp through the Legendre transform for thermo-viscoplasticity. Then we have been discussing for some time over the last few minutes what would be the temperature dependent functions f, which are basically yield functions, which are practically useful and reflect effectively our temperature driven softening, thermal softening effects. So we have seen two such functions. We will be discussing a few more, but we will be also discussing the way in which we will be posing the variational problem within the finite element context in a time discrete manner and solving them, but all in the next lecture. Till then, thank you for watching and goodbye.